Open on slow aerial footage of a 1970s industrial district. Rows of warehouses. Spinning silver domes catching the sunlight on every rooftop. The camera drifts low. For decades, this simple spinning device sat on top of homes, warehouses, and farm buildings across the United States and Australia. It had no motor, no circuit board, no power cable running to the wall. And yet, independent tests showed it could reduce the temperature inside your attic by up to 37 degrees Fahrenheit and cut your cooling bill by nearly 15%. Cut to a modern suburban development. Identical roof lines. Not a single spinning dome in sight. Today, they've almost completely vanished. So the question is, if this device worked so well, why did we stop using it? And more importantly, should we bring it back? If you're new here, this channel is dedicated to engineering solutions that have been overlooked, forgotten, or quietly pushed aside. The kind of knowledge that used to be common sense, and probably should be again. Hit subscribe so you don't miss the next one. Now, let's follow this story back to where it started. Montage. Modern air conditioning units, electrical meters spinning, utility bills on a kitchen table. Every summer, across millions of American homes, the same invisible battle plays out above the ceiling. Solar radiation pounds the roof. The attic absorbs that heat like a furnace. And slowly, silently, it pushes downward, through the drywall, into the bedrooms, the hallways, the living room, forcing your air conditioner to work harder and longer just to fight something it can't even reach. According to the U.S. Department of Energy, every single degree of attic temperature increase can raise your cooling load by up to 4%. In many homes, the ductwork that carries cool air to your rooms actually runs through that superheated attic space, meaning the air is warming back up before it ever arrives. It's a problem that costs American homeowners billions of dollars every year in wasted energy. And the device that was specifically engineered to solve it? Cut to a single whirlybird spinning slowly in a breeze. It's called a turbine ventilator. Some people call it a whirlybird. And for most of the 20th century, it was one of the most common fixtures on rooftops across the country. Then, quietly, it disappeared. To understand why, and whether that was the right call, we need to go back. Not just to the invention itself, but to the centuries of engineering thinking that made it possible. Illustrations of ancient Persian wind towers. Desert city skylines. Narrow mud brick towers rising above the roofline. The idea of moving air through a building without burning fuel or consuming electricity is not new. It is, in fact, one of the oldest engineering challenges in human history. In ancient Persia, architects built tall masonry structures called badgers, wind catchers, designed to funnel desert breezes down into the lower levels of a building while pulling hot, stale air out through the top. Some of these structures are still standing. Some are still functional. In the Tang Dynasty, Buddhist monks integrated natural ventilation ducts throughout underground cave complexes, not for comfort, but for survival. Controlling air quality underground, in spaces housing hundreds of people, was a matter of life and death. By the Middle Ages in Europe, the way a building breathed was considered as important as the breathing of the people inside it. Air was listed among the 4 essential elements, and architects designed accordingly. But all of these solutions were passive, entirely dependent on the shape of the structure and the direction of the wind. Cut to illustrations of coal mines. Torchlit tunnels. Workers pushing carts. The push towards something more active arrived during the Industrial Revolution, and it arrived out of desperation. Deep mines needed continuous airflow to keep workers alive. Engineers responded with fire-driven ventilation shafts and manually powered wooden fans. By the 18th century, the Houses of Parliament in London had installed a primitive mechanical system called a blowing wheel to push fresh air through its chambers. By the 19th century, figures like David Boswell Reed were building steam-driven ventilation systems for hospitals and military barracks, places where the movement of air was the difference between a ward full of patients recovering and a ward full of patients dying. But every one of these systems required fuel, infrastructure, constant maintenance. Pause. Single frame, a rooftop against a clear blue sky, a small spinning turbine head catching the light. The breakthrough came in 1910. An engineer named Samuel Ewart patented a design for a spinning cowl, a dome-shaped ventilator that sat on top of a roof and used the wind itself to actively pull air out of the space below. Ewert's original patent described the device as a solution for ventilation and for preventing the downdrafts that blew smoke back into homes through chimneys. And unlike anything that came before it, his device had no fuel source, no electrical connection, and required no human input of any kind. It just sat there, and it worked. But how? How does a passive spinning device actually pull air out of a building faster than a static vent? Slow motion close-up of a turbine head rotating in a gentle breeze. The answer lies in three separate physical principles, all working simultaneously, and understanding them changes the way you look at every rooftop you'll ever walk past. Simple animated diagrams. Cross-section of a house. Airflow arrows. Let's start with the problem this device is built to solve. On a typical summer afternoon, solar radiation turns your roof into a heating element. The attic beneath it, that enclosed air space above your ceiling, can reach temperatures above 150 degrees Fahrenheit. Not warm, not uncomfortable. 150 degrees. That is the temperature of water that can cause scalding burns within seconds. And that heat doesn't sit still. It radiates downward through the ceiling into the living space below, forcing your air conditioning system to run longer and harder just to compensate. The solution is straightforward. Get that hot air out before it has a chance to radiate down. That is exactly what Ewert's turbine was built to do, and it accomplishes it through three interlocking principles. The first is Bernoulli's principle. As wind passes across the curved aluminum vanes of the turbine head, those vanes force the air to accelerate. And here is the key. When air speeds up, its pressure drops. That pressure drop creates a zone of suction inside the turbine housing, a partial vacuum that actively pulls warm air upward from the attic and exhausts it to the outside. Unlike a static roof vent, which simply sits there and waits for air to drift out on its own, the turbine uses the kinetic energy of the passing wind to drag air out of the building. The faster the wind blows, the harder the turbine pulls. But here is what most people don't know. The turbine doesn't stop working when the wind stops. Even on a still day, it continues to exhaust heat, because it also leverages what engineers call the stack effect, the natural tendency of warm air to rise. Warm air is less dense than cool air. In a building with soffit vents at the eaves and a turbine at the ridge, that rising warm air creates a gentle but continuous pressure gradient. Air pushes upward and out through the turbine, even when the vanes aren't spinning at all. The third principle is the Venturi effect. As air is squeezed through the narrow gaps between the spinning vanes, it accelerates further, and that acceleration causes another drop in pressure, which amplifies the suction cycle already underway. All three of these effects compound one another simultaneously. The result is a device that generates continuous negative pressure at the single highest point of the building, constantly pulling hot, humid, stale air out, and drawing fresh, cooler air in through the soffit vents below. It is elegant engineering, simple to manufacture, simple to install, simple to understand. And the performance data backed it up. Data overlays, temperature gradients, bar charts, field study photographs. The Air Infiltration and Ventilation Center found that installing a turbine ventilator increased attic airflow rates by an average of 15% over a full year, and by as much as 50% when the wind hit the unit from its optimal direction. Field data collected in San Diego showed that a properly installed turbine system could reduce peak attic temperatures by up to 37 degrees Fahrenheit. And that temperature reduction translated to a measurable reduction in energy bills, an average of 14.6% on cooling costs. To put those airflow numbers in real terms, a standard 12-inch turbine moves between 250 and 350 cubic feet of air per minute at just 5 miles per hour of wind. A 14-inch unit pushes that to between 350 and 500 cubic feet per minute. And because the device consumes zero electricity to do this, every single dollar of cooling savings is a pure net gain. For $20 to $100 in materials, plus installation, homeowners in hot climates were recovering their investment within 3 to 5 years, and then running at pure savings for the life of the roof. The numbers were compelling. The engineering was sound. The cost was minimal. So why did it disappear? Pause. Because the story, as it turns out, was more complicated than it appeared. Slow zoom on a rusted turbine head. Frozen in place. One vane bent. The first problem was the one that damaged the technology's reputation most visibly. The defining feature of the turbine, its spinning head, was also its primary point of failure. Inside that spinning assembly were ball bearings. And ball bearings, exposed to the elements year after year, accumulate moisture, dust, and oxidation. Without regular lubrication, they degrade. And when they degrade, they don't fail quietly. They squeak. They grind. They moan in the middle of the night, transmitting that noise directly through the roof structure and into the living space below. Cheaply manufactured units, and the market was flooded with them, were especially prone to this. And over decades, the turbine ventilator earned a reputation not as brilliant passive engineering, but as the noisy, unreliable spinning thing on your neighbor's roof. Cut to animated diagram showing short-circuit airflow. But mechanical noise was only one part of the problem. There was also a more subtle engineering failure that professionals call short-circuiting. Here is how it happens. Turbine ventilators are exhaust devices. They pull air out. Ridge vents, the long perforated strips that run along the peak of modern roofs, are also exhaust devices. Install both on the same roof, above the same attic space, and a problem emerges. Because the turbine pulls more aggressively, it creates a stronger suction than the ridge vent. And in response, the ridge vent stops exhausting air and starts drawing outside air in. Rain, snow, humidity. Instead of managing your attic environment, the two systems start fighting each other. The fix is straightforward. Choose one exhaust system and use it consistently. But here's the reality of the construction industry. Ridge vents are easier and faster to install. They require no penetration through the roof deck, no flashing, no moving parts. And so when homeowners and contractors had to choose, the turbine was usually the one that got dropped. Exterior shot of a modern HOA neighborhood. Identical roof lines. Every shingle in place. And then there was the issue that no amount of engineering data could overcome. Appearance. Turbine ventilators are visible from the street. They sit up on the roofline and spin. In the American housing market, where curb appeal is directly tied to property value, that visibility became a liability. Ridge vents, by comparison, are shingled over designs that are virtually invisible from ground level. Homeowners associations across the country began restricting turbines, and in many cases, banning them outright, because they disrupted the clean, uniform roof lines that define modern suburban aesthetics. Even in Florida, where state law specifically protects the right to install energy-saving devices, many homeowners associations found workarounds, requiring turbines to be placed only on the rear slope of the roof, which, depending on the prevailing wind direction, could reduce their effectiveness to nearly nothing. And finally, building codes began to evolve in a direction that passive systems could not easily follow. As American homes became tighter and more energy efficient, codes began mandating mechanical ventilation systems that could guarantee precise, measurable air exchange rates. Because a turbine's performance depends on variables, wind speed, ambient temperature, roof orientation, that no installer can guarantee, it fell into a regulatory gray area. Difficult to certify, easy to replace with something more predictable. One by one, the conditions that had made the turbine ventilator a standard fixture on American rooftops disappeared. Split screen. A spinning turbine on a Texas ranch house. A sealed, insulated roof on a Minnesota suburban home. So we arrive at the question that matters most. Should you actually use one? The honest answer depends entirely on where you live and what problem you are actually trying to solve. If you are in a hot, windy climate, the Gulf Coast, the American Southwest, the Sun Belt, a turbine ventilator remains one of the most cost-effective attic ventilation solutions available. A 12-inch unit costs between $20 and $100. Professional installation adds between $100 and $300, depending on roof pitch. For a standard 1,500 square foot attic, 2 units is generally sufficient. In a southern climate, energy savings can recover that investment within 3 to 5 years. And because proper attic ventilation prevents shingles from overheating and stops moisture from rotting the roof deck, the turbine can actually extend the functional life of your roof. But there are situations where a turbine is the wrong tool entirely. In cold climates, internal moisture can freeze the vanes solid, shutting the system down in winter, which is also when pressure imbalances can drive cold outside air into your living space. In a modern, highly airtight home where a mechanical ventilation system is already managing air exchange rates precisely, Adding a passive exhaust point can disrupt the pressure balance the entire system was designed to maintain. And for homeowners building new or re-roofing, particularly in moderate climates, a full-length ridge vent is often the more practical choice. A continuous ridge vent running the full span of a standard roof provides over 900 square inches of net free ventilation area, roughly double what three 14-inch turbines deliver, distributed evenly across the entire ridge, eliminating the dead zones that concentrated turbine placement can create in the corners of an attic. No moving parts, no bearings, no noise, no HOA letters. It just sits there and works. Wide shot. A hot Texas afternoon. A single turbine spinning steadily in the wind. Slow fade. Samuel Ewert's 1910 invention wasn't a gimmick. The engineering was real. The performance data was real. And for millions of homes in hot, windy climates, the turbine ventilator remains exactly what it was a century ago. A clever, zero-energy solution to a problem that costs homeowners real money every single summer. What changed wasn't the physics. The physics still work exactly the same way they always did. What changed was the world around it. Mass-market manufacturing lowered quality. Subdivisions optimized for aesthetics. Building codes evolved toward precision and certification. And an industry settled on the path of least resistance. The invisible ridge vent, rather than the spinning dome that required a bit more thought to install correctly. The turbine ventilator didn't fail because it stopped working. It disappeared because the conditions that rewarded good passive engineering gave way to conditions that rewarded convenience, uniformity, and aesthetics. Whether that trade-off was worth it, that's something worth thinking about the next time you open your utility bill in August.